out and becoming smaller? What do you think? Flatter, they're flattening out, which means smaller and smaller positive numbers, right? So as I draw my derivative over here, I should draw points that are above the x-axis, right? But they get smaller and smaller and smaller. So I should expect to see something like this. See, I'm not trying to be super precise here. I'm just trying to get a feel of what's going on. What about over here, though? Something really interesting happens here. Can you all tell what's happening to those tangent lines? It's getting steeper. I think what I'm going to do is go to Desmos and graph that function. This is the graph that we're looking at right here. I'm zooming in on it. Can you all see what's happening here with these slopes? Steeper positive, right? Steeper positive means bigger positive numbers. And then what happens if I actually get to this point? What happens? It wants to become vertical, right? And what's the slope of a vertical line? Slope of a horizontal line is 0, right? Positive slope, negative slope, 0. What's the slope of a vertical line? Undefined. So what we should expect is to be undefined. Our derivative will be undefined at 0. Let me go back to my picture. So I know that as I move to the left, right, as I move left towards here, there's going to be no graph over there, but I know as I move this way, these things are getting bigger positive, so my graph should go like this, and it just tries to become almost infinite slope. So there's a vertical asymptote there. The blue graph is the derivative of the red one. I think y'all are getting this. I don't know. All right, why don't you try this? See if you can. What you're looking at here is the graph of the sine function. And I want you to see, go ahead and, I'm not going to collect this, but see if you on your own can draw the derivative of that. Just do your best. I'm going to give you a few minutes. Whoa. Uh-oh. If you're having trouble getting started, my suggestion to you is to always start by seeing if there's somewhere on that graph that you know for sure what the derivative is. Which my hint will be those points there. You can actually tell me what the slope of the tangent line is there. And then from there, try to build out what the rest of it would look like. I'm going to give you like 5 minutes, and I'm going to step out. I'll be back. Who thinks they have something? Just show of hands. I want to see where people are. Only a few? Couple? Yeah. At these points, you should have a zero slope. So the derivative would be zero, which means you would have an x-intercept on that derivative, right?
Yes.
Okay. So is that what you have? You have like a point here, and a point here, and a point here, and a point here. Everyone should have that for the derivative so far, right? I'm just going to go another minute, and then we'll work through this together. All right, I'm going to walk through this. All right, so if you're hung up on it, you might want to pay attention. So first thing that I'm noticing is that at those black points, here, 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 at those black points right there, I know that the slope of the tangent line there is 0. You can see it there. My slope is 0 there. My slope is 0 there. My slope is 0 there, right? That means that when I draw my blue curve, right, my derivative, the y value of the curve or the function should be 0 at those points. So at this x value, I should get a 0. This x value is 0, a 0, and a 0. So I'm starting with that. Now what I'm going to do, let me back this thing up. Let me go back to this one. And I imagine that if I move to the right, if I just go to the right a little bit, like right there, I'm going to get a small, because it's just barely pitched down, a small, what, positive or negative? Small negative, right? And as I move to the right a little bit more, it's going to become a bigger negative number. And then bigger, and then I get to about right there. And that's about as big negative as I'm going to get. Because as I move closer, it starts to flatten out again, doesn't it? Still negative slopes, but they're smaller. So my derivative should start out with small negatives, right? Small negatives, get to some maximum negative number, and then go back smaller negatives. Did I say small? Small negatives getting bigger, get to a maximum negative number, and then back to small negative numbers back to 0. So it's going to look like a little loop on the bottom, right? So it'll look like this. Okay. Now, once I get to here and start moving to the right, what type of slopes do I get there? Little small positive, bigger positive, until I get about right there. That's the max positive I'm going to get. And then they stay positive, but they get smaller. And I go back to 0, right? So small positives getting bigger positives, hit a maximum, come back down, positives to 0. So it looks like this. And then when I do this piece right here is exactly the same as this piece right here. So I'm just going to repeat myself, which you should expect with a sine curve, right? Because it's periodic, it just keeps doing the same thing. And that's it, that's the graph. Does anybody know what function that looks like? Cosine. That looks like the cosine function, doesn't it, kind of? Right? Remember back in pre-cal, sine of x looks like this, and cosine of x looks like this. So it turns out that it is cosine, but I'm just trying to get you to see, like, it kind of does look like cosine. We're not totally sure of that right now. All right. Do y'all feel like I've done enough of these where you're ready to try this on your own homework-wise? Yeah? Okay. All right, then we're moving on. I'll leave that over there. All right, when it comes to this idea of a derivative, right? It's such an important thing in calculus and in mathematics and applied math, no matter what branch you're in, this idea of taking a function, taking its derivative, right, and creating this new function. This whole concept is critical to us. So we have different notations that we use to let people know that I would like for you to take the derivative of a function. The first notation we've learned is this notation. So if we're given y equals f of x, okay, so if I give you y is some function of x, like maybe I'd write down, for example, y equals x squared, or maybe I write down f of x equals x squared, right? So if you're given something like that, where I give you the function, right? Then if I want you to find the derivative, if I want you to actually go do this thing, that limit, I want you to do this right here, then what I'm going to write is this, f prime of x. Now that notation you've seen before, yes? There's a bunch of other notations though. If you ever see this, go take the derivative, go do that limit. Or I can say dy over dx. This is new notation. In the beginning of this class, I told you I think that there were two people who created calculus, Isaac Newton and Leibniz. His last name is Leibniz. This is the notation that Leibniz used, and Newton used a different notation. So this is called Leibniz notation. This is our regular notation we use in here. And then there's a bunch more. All right, so instead of me writing them all down, I'm just going to bring up the notes. These are all the same thing. So this is in your notes, so you don't necessarily need to copy this all down. But from now on, if you see y is some function of x, that means take the derivative. Okay? Y with the little prime mark means take the derivative. Dy dx means take the derivative. df over dx means take the derivative. All of these mean the same thing. All right? Now I know that seems like a lot of things to keep track of, but the ones that we are going to use primarily in this class are this one, this one, this one, and that one. Those are the three that we use almost exclusively in this class. If you ever need to take like Cal 3, then you'll need this notation right here. And this notation as well. But if you're going to be Cal 1, Cal 2, you're going to mostly see those four right there. Those mean the same thing. So the way that I think about this is, you know, if I read this, this is just f prime of x, right? Just means take the derivative of the function at x. This means, hey, take the derivative of that y function, all right? This means, hey, take the derivative of the y function, treating x like your variable. This means, hey, take the derivative, treating x like your variable, of that f function. There's like different ways to say the same thing. They all mean the same. So I talk about Leibniz notation here, the dy dx. Gottfried, I can never remember his first name. Gottfried and Isaac Newton were the two fathers of calculus. All right, so now some language, some definitions for us. The derivative is a limit, isn't it? It's a limit, that's all it is. Limits sometimes do not exist, right? We've had problems before. On your test, you had problems where your answer should have been does not exist. It's possible to have a limit not exist. So this definition says a function f is said to be differentiable at some point a if the derivative exists there. Right, so if the derivative exists, we say that that function is differentiable. If it's differentiable on an open interval, right, that means it's differentiable at every point in that interval, then we say it's differentiable on the interval. Here's a theorem. If your function is differentiable at a point, then it must be continuous. Remember, continuity meant you draw it without picking up your pencil? If I'm telling you that the derivative exists at a point, then I'm telling you that you have to be able to draw without picking up your pencil at that point. We're not going to go through this theorem in depth. All right, when does a function fail to be differentiable? So there are times when you cannot find a derivative. And so there are three different cases we will run into. And here's what they are. Either you're looking at a corner or a cusp, or there's a jump in the graph, or there's a vertical tangent line. Those are your three things that can screw up the differentiability. So here are pictures. Look at that graph right there. If I asked you to draw the derivative of this, right? If I ask you to draw the derivative, here's what you would draw. The green is the derivative of that. Because to the left it's a straight line, so the slope over here is always the same slope. And then over here it's a straight line with negative slope, so the derivative is always a negative. And do you see that there's a break here? That means at zero, the derivative doesn't exist. We actually have a hole here and a hole here. Do you all see that that corresponds to that corner? Anywhere you have a corner or a cusp, you cannot have the derivative, all right? Corner or cusp. Now, what does a cusp look like? Do I have a cusp here? I don't have a cusp. Let me draw you a cusp, because a lot of students don't know what a cusp looks like. A cusp is something like that. That's a cusp. This function would fail to be differentiable at that point right there. The way that I think about it is this. If I'm thinking about the slope of the tangent line, watch what happens. Right here, do you see my slope is always the same, right? The slope of the tangent line is always the same. And then what happens at this point? It goes from positive to negative immediately, doesn't it? And that rapid switch screws the derivative up. Same with this cusp. My derivative is what? Positive, 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 positive. And when I get to that point, it has to go immediately to negative, right? That messes up the derivative. If you have something like this, here you don't have that same problem, because notice that it's a gradual changing of that slope, right? The slope is gradually becoming 0 and then rolling over and coming back down. The derivative has no problems at those humps like that. It has problems at corners and at cusps, right? That's your first type of problem with derivatives. Your second is anytime you have a jump. If you have a break in the graph, then you're not continuous there, right? This is not continuous at that break. And to be differentiable, you have to be continuous. So anytime you have a jump, break, you don't have continuity. Differentiability. And then anywhere you have a vertical tangent. This one's a little tricky. Look what's happening to the derivative here. My derivative is going to come through. It's going to be positive, positive, positive. But look what happens here. What is it trying to do? It's trying to become vertical. And what's the slope of a vertical line? We just said undefined. And that means that this derivative would not exist. And so at that vertical tangent point right there, at this point, we would have a problem with the derivative. Those are the three different things that can cause problems with differentiability. That's a good test problem, right? List the three different, issues that could create problems with the derivative, right? Corner cusps is one. The other one is jumps or breaks in the graph. And the last one is vertical tangents. So mathematicians are weird. Okay, we're weird creatures. For a long time, there was this question mathematicians asked. They said, okay, is it possible, does there exist a function that I can draw without picking up my pencil, but I can't take the derivative anywhere? Does that seem like a reasonable question for someone to ask? Like, is there a function out there that you can start drawing it, right? But if you try and take the derivative anywhere, the derivative won't exist, right? So mathematicians went, I don't know, let's, maybe. I mean, can you think of a function? Like if I draw this function right here, those are corners. Do you all agree that at every one of these sharp corners, my derivative would not exist? But there's a bunch of places it does exist, right? In between these little line segments, my derivative is fine. It's just at these corners. And notice I could draw that without picking up my pencil, right? So mathematicians were like, is there a function you can draw without picking up your pencil, but no matter where you go, you have an issue with the derivative? And so we went looking and looking and looking, and this guy Weierstrass was the one who came up with it, all right? And it's called the Weierstrass function. And this is an example of a function that you can draw without picking up your pencil, but is nowhere differentiable. Nowhere on this function does a derivative exist. And here's what it looks like. And it's really, really crazy to understand what this function's doing. But think about it like this. What it is it's like this, okay? So do y'all agree I'm not differentiable here, 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 right? But if you were to look at this edge, it's actually not a straight line. This edge, if I were to zoom in on it, that edge actually looks like this. Like a saw blade, two teeth on a saw blade. That's what this edge looks like. And so it's not differentiable at each one of those little corners. But if you zoom in on any one of these, it's a little saw blade. And if you zoom in on any one of the teeth, it's a saw blade. And you can do that forever. No matter how far you zoom in, it's always saw blade teeth. It's weird, right? It's a weird function. But mathematically, it's a well-defined function. And you can plug values of x in and get a point out. But the problem is if you try and find the slope of a tangent line, you're going to get the derivative to not exist. Now, do y'all want to see what the function actually looks like? And not the graph, but do y'all want to see what the definition is? Because, like, if I ask you to graph x squared, you know that draws a parabola, right? Would y'all like to see the actual algebraic function for that or no? Yeah, it's crazy, but I'll show it to you. How many of you have to take Cal 2? Cal 2? Yeah, well, okay. We won't study this in Cal 2, but I probably misspelled this, but I don't care. Leave the site. There it is. So this is the function right here. If you're not familiar with this notation, then you're not going to know what it means. But this means you're going to take the sum from n equals 0 all the way to infinity of this expression. So what you do first is, let me make A1, so that goes away, and let's make B1 as well. No, I have to have, they can't be 1. Hold on. Well, I'll just leave A and B whatever they are. So what you do is you first replace n with 0 and figure out what that is, and then you add to that, replace n with 1, and then add to that, replace n with 2, and add to that, and you do it forever. So what this is basically a string of cosine functions that go on forever. And if you plug a number in, you just plug it in, and then you have to plug it into this list of infinitely many cosines, and that gets you the Weierstrass function. Now you might be saying, well, how do you ever define a function to be an infinite number of things, right? Well, in Cal 2 we study these things. These are called series. It's chapter 8 in Cal 2. And so when we study series, we'll understand that this actually has good meaning and that it's well defined. So we're ahead of ourselves to actually try and understand what the function is. But if we graph it, we get that weird saw blade thing. All right, moving on. You're not going to be tested on the Weierstrass function. It's just random information for you. All right, doing okay, 9 minutes. My goal is to just finish this section today, so let's hang in there. All right. If we have this idea that we can start with the function and take its derivative, right, and get this new function, that's like the main idea today, what is stopping me from taking this function and taking the derivative of that function? Because that's just a function now, right? Started with the function, I took its derivative, got a new function. So let's just act like we started here now and ask you to take derivative of that, could you? Right? It's just a function, so you could do derivative of that. So if I do the derivative again, I get what we call the second derivative, and that will be f with 2 primes on it. And is there anything stopping me from taking that function and doing derivative again? No, right? And I could do this many times I want to do, right? So we have this idea of higher order derivatives, which just means taking derivatives of derivatives and then just repeating the process however many times you want to do it. Now, it will have meaning to us in a minute, but I mean, in a few sections we'll actually, right now we kind of know what the relationship is between these two, right? Like this function tells you about the slope of the tangent line here. The question will be, what does this tell you about the original function, right? What does it tell you? Is there some connection with the graph? And it turns out there is, but stay tuned. Right now we're just defining what it means to be a higher order derivative. And this is me just saying exactly what I just said, right? Since f prime is a new function, we could just take derivative again. And so we have a special notation for taking the derivative repeatedly. We know that f prime of x is the first derivative. If I do f double prime, that means you're taking the derivative of the derivative. That's called your second derivative. If I do f triple prime, 1, 2, 3, that's the derivative of the second derivative, which gives you the third derivative. That making sense with this notation? First derivative, second derivative, third derivative. What do you think? Fourth derivative, am I going to do 4 primes? Probably better if I did something like this. F with the 4 in parentheses, it must be in parentheses. That means you're going to take the derivative 4 times. That's your fourth derivative. And then fifth derivative, and sixth, and so on. The reason we don't use this notation is that if you write this, what this means is you taking the f of x function and you are raising it to the 4th power. That's this notation. That's f of x times itself 4 times. We don't want to do that. That's not what the derivative is. So we use the parentheses around the 4 to let you know we're talking about derivatives here. You all see the difference between those? Fifth derivative, 6th, 7th, 8th, 9th. There's no limit to how many derivatives you can take, and so on, right? Now, all of this notation I used right here was using the classic calculus notation. Let me show you what the higher order derivatives look like using Leibniz notation. Leibniz notation, the first derivative, we just write dy dx. That means take the first derivative. If I want you to do the second derivative, what we do is we write a d superscript up here, 2y, on the bottom dx, and then the 2 up here like this. Notice that the 2's are offset, right? They're not lined up together. That's intentional. Because if somebody writes this down, if you write that, somebody might think what you mean is this. Does that seem reasonable that this would mean this? And this means take the derivative and do what with it? Square it. And I don't want you to do that. So I don't want to use this notation and you accidentally think this. So what we do instead is we offset the 2's so that you don't think I'm squaring. And that tells you the second derivative. And then the third derivative. And then the 4th and 5th and 6th and 7th and so on and forever, amen, right? Got it? All right. So remember, we talked about this already, that if you have a function that gives you the position of an object, right? Then the derivative, the first derivative gives you the instantaneous velocity of the function, or sorry, of the particle. So we already know, because we talked about a previous section, that if you have the position function, the derivative gives you the velocity. But if you take the derivative of the velocity, that's the second derivative, then what you get is the acceleration function. Let me see if I have an example of this. I don't have. We'll do an example in further sections. Okay. So I think that's it for this session. I think we can wrap this up. We only have 2 or 3 minutes left. Make sure you do the homework here. What we're going to do next class, right, on what, Thursday, is you know how we've been using this limit to find derivatives and it's kind of a pain in the butt? We finally are ready to shed the limit away from us, and I'm just going to give you the shortcut rules on how to find derivatives. It's going It's going to make finding derivatives a lot easier for us because there will be no limits involved. But then there's a catch to it. If it's going to be easier to find derivatives, then the functions that we're actually going to look at are going to get harder. They're going to get more complicated. So then the rules we have get harder to use. But we're getting rid of the limit, so that's good news, I think. All right, everyone, have a good day. If you have any questions on your test or anything like that, I will hang out. Pardon? The homework is whatever's on the schedule here. So for what is this? 2.2, it's these problems right here. It's a lot of problems. You're supposed to do as much as you can to feel comfortable with the concept, right? Like, if you don't have to do every single one of these. Just do enough where you feel like, okay, I get it. All right, y'all have a great day. 2.3 when we come back. Let me turn my camera off real quick. Okay. Go ahead. Whoa, whoa. Easy now.